Have you ever wondered how machines make decisions, like classifying emails as spam or not spam, or recognizing handwritten digits? What if I told you there's a fascinating mathematical approach behind these tasks, called support vector machines, or SVM? Today, we're going to demystify SVMs in a way that's simple, engaging, and most importantly, easy to understand. In the end of this video, you'll understand how SVMs work, what makes them so unique, and how they can handle complex classification problems. Let's jump right in. First, what exactly is a support vector machine? At its core, SVM is a classification algorithm designed for binary classification tasks. It's built upon the concept of a maximal margin classifier, which aims to find the best possible boundary, or hyperplane, that separates data into two classes. But here's the catch. The maximal margin classifier only works if your data is perfectly linearly separable, which rarely happens in real-world scenarios. That's where the support vector classifier comes in. It's an extension that can handle cases where data isn't perfectly separable by allowing for some flexibility or misclassifications. And then, taking it a step further, the support vector machine adds the ability to work with nonlinear class boundaries. It's like upgrading from a simple car to a high-performance race car. Let's talk about hyperplanes because they're at the heart of SVMs. Imagine you're working in a two-dimensional space. Here, a hyperplane is just a line that separates your data into two categories. Easy, right? Now, if we move to 3 dimensions, the hyperplane becomes a flat, two-dimensional plane. But what happens when we go beyond 3 dimensions? While we can't visualize it, a hyperplane in higher dimensions is a flat p-1 space that divides the data. Data points that don't satisfy this equation fall on one side of the hyperplane, and others fall on the opposite side. Essentially, the hyperplane splits the space into two halves, helping us separate the data into distinct classes. Here's how classification works. Imagine you have data points in a multi-dimensional space, and each point belongs to one of two classes, like -1 or +1. A hyperplane that perfectly separates these classes would satisfy this rule. The best hyperplane ensures all points are correctly classified and lies as far away as possible from the closest points of both classes. These closest points are called support vectors. So, what's the maximal margin classifier? It's a hyperplane that maximizes the distance, or margin, between itself and the nearest data points from either class. Points on the margin, or close to the margin, are called as support vectors. Why does this matter? A larger margin generally means better generalization to unseen data. However, if your data isn't perfectly separable, you can't use the maximal margin classifier. That's where we turn to, the support vector classifier, also known as the soft margin classifier. Instead of trying to perfectly separate the data, this method allows some points to violate the margin. Consider following example. In the left panel, most of the observations are on the correct side of the margin. A small subset of the observations are on the wrong side. Observations on the wrong side of the hyperplane correspond to training observations that are misclassified. Here's where the concept of slack variables comes in. If a point is on the correct side of the margin, the slack variable for that point is 0. If it's on the wrong side, the slack variable is greater than 0. If it's even on the wrong side of the hyperplane, the slack variable exceeds 1. The amount of violation we allow is controlled by a tuning parameter, c. Think of c as the flexibility knob. A small c means less tolerance for violations, leading to narrower margins. A larger c means more tolerance, allowing wider margins. All right, so far, we've talked about how SVMs use a hyperplane to classify data. Pretty cool, right? But what happens when the data isn't neatly separable by a straight line or plane? Let's dive into nonlinear boundaries. Imagine you're trying to separate two types of objects on your desk, but they're not in two distinct groups. Instead, they're scattered in a circular pattern, with snacks forming an outer ring and books in the middle. Can a straight line separate them? Nope. A linear boundary just won't cut it. This is where SVM gets super creative. To handle this, SVM uses something called the kernel trick. Think of it like adding a new dimension to make the data separable. These are mathematical tools that help us map the data into a higher dimensional space without actually calculating all the coordinates, because that would be computationally expensive. Some common kernel functions include linear kernel, best for simple, straight-line separations. Polynomial kernel allows for curved boundaries. Radial basis function kernel, popular for complex, circular, or nonlinear patterns. Think of these kernels as magic lenses that help SVMs see the data differently. Finally, how do we evaluate an SVM model? There are two common techniques. Validation set approach. Split the dataset into a training set and a testing set. Train the model on one and evaluate it on the other. Cross-validation. Divide the dataset into multiple folds and ensure every part is used for both training and testing. For evaluating the above-discussed metrics, a special tool is used, which is called as confusion matrix. Consider the following example, where we have to predict a categorical variable with two levels, yes and no. Consider that we have predicted 100 testing observations using a trained model. And that's a wrap on support vector machines. From hyperplanes to soft margins and nonlinear boundaries, SVM is a powerful and versatile algorithm for classification tasks. I hope this explanation helped you understand how SVM works and why it's such a popular choice in machine learning. If you enjoyed this video, don't forget to like, subscribe, and share it with others exploring the world of data science and AI. See you next weekend with another exciting topic.